Hello and welcome back to Counting Rocks, an introduction to combinatorics at CSU. Today we're going to be talking about the principle of inclusion-exclusion and how we can use it to solve combinatorics problems. So here's a very simple example of a problem that we would use the principle of inclusion-exclusion to solve. In a class of 20 people, 15 like chocolate ice cream, 14 like vanilla, and only 1 likes neither flavor. How many like both? Now we don't need the principle of inclusion-exclusion to solve this problem, but for more complicated problems of this form, we will. So one way to model this problem is with the language of set theory that we introduced in the last video. Let's think of a set of all people who like chocolate in the class as the circle labeled C, and the set of all people who like vanilla as the circle labeled V, and draw a Venn diagram with their overlap, and we're trying to find how many like both, how many people are in this intersection. Let's call X, Y, and Z the number of people in each of these regions. So X is the number of people who like chocolate but not vanilla. Y is the number of people who like both. Z is the number who like vanilla but not chocolate. So with this setup, we see that X plus Y is 15 because X plus Y is the total number of people who like chocolate ice cream, and the problem says 15. So X plus Y is 15, Y plus Z is the number of vanilla, so that's 14. And we know X plus Y plus Z is the total number of people that like some amount of ice cream, and what the problem says is one likes neither. So I'm imagining 20 people and one point is out here and not in any set, but then the other 19 are in these sets somewhere. So X plus Y plus Z is 19. And if you solve these equations for X, Y, and Z, you'll find X equals 5, Z equals 4, and Y equals 10. So this is one way to solve this problem. There are 10 people who like both chocolate and vanilla in this setup, and we didn't need any fancy principle, we just needed a Venn diagram, a little bit of set theory, and a little bit of logic. So let's talk about this setup in general. If we have a Venn diagram, A and B, and we have the numbers X, Y, and Z as before, the size of the set A, the cardinality of A, is X plus Y, the size of B is Y plus Z, and the size of the union of A and B is what also came up in the problem, which was X plus Y plus Z, and A intersection with B is just Y. So we had union and intersection in the last video, and that's one way we can phrase this problem in terms of finding the intersection between two sets. If you generalize what we did on the previous page, we'll notice that there's a relation between these four set sizes, which is the size of A plus the size of B. If you add them together, you'll get X plus 2Y plus Z. And if you add these two together, you'll also get X plus 2Y plus Z. So we get this equation, size of A plus size of B equals size of A union B plus the size of A intersect B, which leads to the principle of inclusion-exclusion, which says the size of A union B, if we solve this equation for this element, is the size of A plus the size of B minus the size of the intersection. This equation allows us to solve for any one of these set sizes if you know the three others. And so if the problem gives you the three others, you can just plug them in and solve for the fourth. So let's redo this problem using this principle. Again, in class of 20 people, 15 like chocolate, 14 like vanilla, and 1 likes neither. So 1 likes neither is saying that the union of the sets chocolate and vanilla here is 19. And the set C has size 15 and set B has size 14, C for chocolate and V for vanilla. And we want to calculate the size of the intersection C intersect V to see how many like both chocolate and vanilla, because intersect means and. And so you plug it into the principle of inclusion-exclusion. We have 19 equals 14 plus 15 minus whatever we're trying to find, and we solve for that as a variable, and we find that it equals 10. So that's another way of solving this problem, and it's a little more systematic than what we did before with X, Y, and Z. Now let's try to generalize, and here's where you want the principle of inclusion-exclusion and not just try to solve it directly. In the class of 20 students, say 15 like chocolate, 14 like vanilla, 11 like strawberry, but on the poll you'll find that 12 like both chocolate and vanilla, 7 like both vanilla and strawberry, 8 like both chocolate and strawberry, and only one of them doesn't like any ice cream at all. So that's one outside the box again. There's still 19 inside these circles. Now we have a circle for chocolate, a circle for vanilla, and a circle for strawberry. We've expanded the poll. And we want to know how many like all three, given this data. You can actually figure it out just from this data. And let's talk about the general principle of inclusion-exclusion for 3 sets. So it's called inclusion-exclusion because we're including some things and then excluding by subtracting some other things. In particular, to calculate the size of the union of A, B, and C, the union of 3 sets is just going to be all the things inside all these circles union together counted exactly once. We want to count elements in here exactly once and elements here exactly once and so on. So what we can do is first do a bit of an overcount, where we count the size of A plus the size of B plus the size of C. That's this first line. but we've overcounted some of the elements, in particular the things in the intersections of A and B, and the intersection of B and C, and the intersection of A and C. These were all counted twice. So let's subtract one copy of each. We'll subtract A intersect B, and subtract A intersect C, and subtract B intersect C. Now, these little regions are going to be counted exactly once, but the region on the inside, let's think how many times we've counted that. That's in all of the sets we've listed so far. So we've counted it 1, 2, 3 times, and then -1, -2, -3. So we've actually counted it 0 times, and so we have to add it back. So you add back the intersection of all 3. And you notice the pattern is, first we add all the sizes of the sets, then we subtract all the intersections of pairs of them, then we add back the intersections of 3 of them, and so on, and this generalizes to any number of sets. So let's use this principle now to solve our problem. So in the problem I gave, 15 like chocolate, so we can say A is the set of all people who like chocolate, B is the set of all people who like vanilla, C is strawberry. So size of A was 15, size of B was 14, size of C was 11. It gave the sizes of the number of people who like, say, chocolate and vanilla was 12, and then we similarly have 7 and 8 for the other 2 intersections. And we know the union of all the sets is 19. So we can plug in the 19 up on the left here, and then plug the other numbers in for A, B, C, and the intersections of the pairs, and then we just have this intersection left that we can solve for. Let's see what this looks like. 19 is 15 plus 14 plus 11 minus 12 minus 7 minus 8 plus x. Let's let x be what we're looking for. And you solve for x, and you find x equals 6. So we found that there are 6 people who like all 3 given this poll data. So let's do a slightly more complicated example of where the principle of inclusion-exclusion comes up without just doing Venn diagrams and polls. Counting derangements is a classic combinatorial problem. It's also known as the hat check problem, where people's hats all get mixed up. Derangements are basically rearrangements where everything gets as mixed up as possible. And the question we can start with is how many rearrangements or permutations of 1, 2, and 3 change the position of every number? So 1, 2, and 3 are already in order here, but if you mix them up, say 2, 3, and then 1, then 1 should be in the first position, but it's not anymore. 2 should be in the second position, but it's not anymore. 3 should be in the third position, but it's not anymore. So this is an example of a derangement. It's a rearrangement that doesn't fix the position of any number. This is another derangement of 1, 2, and 3. Let's see how many there are total. How many permutations do keep 1 in the same position as itself? Well then, you either keep 2 and 3 here, or you switch 2 and 3. So there's 2 factorial, or 2 permutations, that fix 1. There's 2 permutations that fix 2, and there's 2 permutations that fix 3. Let's let A, B, and C be the sets of these permutations that fix 1, 2, and 3. They do have some overlap. You'll have to calculate the sizes of the intersections of A and B, and the intersection of A and C, and the intersection of B and C. Well, that's basically just counting how many permutations fix 2 of the numbers. If we fix the positions of 1 and 2, and we make sure they stay there, well then the 3 has to go there, so actually there's only 1 possibility. So there's 1 possibility for each of the intersections, and only 1 permutation fixes all 3, 1, 2, 3. And so we can use the principle of inclusion-exclusion to find how many permutations do fix at least some element, that they don't move it. So we add the 2's, 2 plus 2 plus 2, we subtract the 1's that are the intersections, minus 1, minus 1, minus 1, and then we add back that 1. This is what the inclusion-exclusion principle says is the size of the union of A, B, and C. So the size of the union is 4, so there's a total of 4 permutations that do fix some element, and then there's 6 permutations total, so by the subtraction principle, there are 6 minus 4 derangements, or 2, meaning we already found both of them. Now let's see how we can generalize this for derangements of 4 elements, or 5. Well, the generalized principle of inclusion-exclusion is what I've hinted at before. You have the union of 4 sets here, for instance, is the sum of the sizes of the 4 sets minus all the sizes of the intersection pairs, which there's 6 of them now, right? 4 choose 2 is 6. And then you add back the intersections of 3 at a time. A intersect B intersect C, A intersect B intersect D, etc. There's 4 of those. And then you subtract the intersection of all 4. And keeping this formula in mind, let's look at derangements of size 4. So we can use this generalized principle to count now how many rearrangements of 1, 2, 3, and 4 change the position of every number. How many derangements of 4 items are there? Well, the first element can't be 1, and the second element can't be 2, and the third element can't be 3, and the fourth element can't be 4. So here's an example of a derangement, here's another example of a derangement, but there are a lot more than 2 in this case. So how many are there? Well, one way to approach this problem is to count the complement. How many do fix some number? That's a little easier to get a handle on, but we'll need the principle of inclusion-exclusion. So to count the complement, how many do fix something? There are 6 permutations that fix, say, the first digit. If we make the first digit be 1, then there's 3 factorial ways to rearrange the remaining 3 numbers. Similarly, if we make the second position be 2, then there's 3 factorial ways of rearranging the numbers. But we've overcounted, because if we fix both 1 and 2, that was in both of those sets that we counted. So we need to subtract how many fix any given pair for each pair of numbers. And so, for instance, if we fix 1 and 2, then there's 2 factorial ways of rearranging 3 and 4, and same for any other pair, like 3 and 4, or 1 and 4, or anything like that. And then, if you fix 3 of the numbers, we'll need to add those back. So what if we fix 1, 2, and 3? Well, then actually 4 is determined. Only the permutation 1, 2, 3, 4 fixes 3 of the numbers, and similarly, only one permutation fixes all 4. So we can use the 4-set principle of inclusion-exclusion to say, well, there's 4 sets that each have 6 elements in them. We're going to add those together. And then there's 4 choose 2 intersections where they contain a certain pair that's fixed, and there's 2 factorial ways for each of those, so we subtract those off. Then we have to add back the ones that fix 3, so 4 choose 3 times 1, and then finally subtract that 1 that fixes all 4, and we get 15 when we calculate this all out. And finally, that's the complement, so we take 24 minus 15. 24 is the total number of permutations of 1, 2, 3, 4 factorial. Minus 15 is 9. So there are 9 derangements of 1, 2, 3, and 4. And you can try to find them all on your own. But now you try a problem that uses principle of inclusion-exclusion, but only for 2 sets. So it's going to be a Venn diagram with just 2 sets, and it is in terms of permutations, though, and related to the derangement problem that we just did. How many permutations of 1, 2, 3, 4, and 5 do not fix the positions of 1 or 2? And that's all for today, and I'll see you next time.